This is part 2 of trying to calculate what my uncertainty in position is for this wave function, which corresponds to a Gaussian. In the last video, we normalized it and started setting up how to calculate the expectation value of x squared. And I talked through the approach, didn't fully do out the integral. This is your final answer. So now, let's calculate my expectation value of x, which we then square. So again, this is going to be my wave function, x wave function. So pretty similar to before. Now, and I'm going to kind of skip the step. I'm going to go ahead and bring out that 2 over pi a squared, and we'll know that will be to the 1/2 because I'm going to have 2 wave functions. So that I'm then left with x e to the negative x squared with a 2, because there's 2 of them multiplied by each other, over a squared dx. Okay, you might think, okay, let's turn to our table of integrals. What do I have? I have x, e to the something. Well, I have f21, which is x to the n. Oh, but that's e to the negative x. So I see one that looks pretty similar, and okay, again, it's a 0 to infinity, so let's try to use a symmetry argument. Now, if you think, Dr. Ackerman, why are you being silly? This is the point. There's something here to look at first before you turn to your table of integrals, right? This function has even symmetry. It's still just a version of a Gaussian. Ooh, terrible Gaussian, but you know what I mean. What's this function? Well, it has odd symmetry. So if we multiply an odd function by an even function, you get an odd function, right? So I can kind of say that just qualitatively e to the negative 2x squared over a squared. If I sketch out what this looks like, kind of I say, okay, here's my x equals 0, and there's my axis. What does this look like? Well, over here it has to be negative. So it's going to come down, go up, but then it has to go through 0. And it does something like that. This integral, and again, if you look, it's odd symmetry. This integral is negative the integral of this one. So if I was just taking my integral from 0 to infinity, that would be a positive number. My integral from negative infinity to 0 is a negative number. Those are equal and opposite. So from symmetry arguments alone, I get to say that this is equal to 0. So please, when you're doing out your work, don't forget to think about symmetry. And when you get to a point like this, that you can in fact make a symmetry argument for why this integral is 0, don't just write equals 0 and leave it without comment. Say that it's by symmetry. In this case, I drew out the picture, right? I'm showing some work here. Please, please, please actually indicate why it's equal to 0. For all I know, you punched it into your calculator and got 0. Okay, I guess that's valid. But do, when you are using a symmetry argument, make it clear what you're doing. Okay, so if the expectation value of x is 0, that also makes sense, right? That's kind of saying, what's the average value of x from this function? Well, 0, it's symmetric. So what that means is our expectation value of x squared is equal to 0. Because that's actually the term that's in here. So when I go to calculate what this uncertainty is, right, that first term was a squared over 4. And then the second term is 0. And so what you just get is the square root of a squared over 4, which is equal to a over 2. That's what our delta x is for this wave function, which is a Gaussian. Now, depending on what math you've studied, possibly you've studied some properties of Gaussians before, and this would actually be the definition of the uncertainty of a Gaussian that is written in this form. So this should check out if you know much about Gaussians, but please, if you're asked to calculate what the uncertainty is, don't just look at it and say, well, I know how a Gaussian works, it's this. Like, do out the math, because that's what we're trying to practice. But in this case, it does make sense that that's what we get. So I'm going to stop here. You could also imagine going through and saying, well, what's going to be the expectation value of the position operator squared. Remember, then you actually have some derivatives to work with. It's a little bit messier. You also are going to have then the position operator finds the expectation of that squared. So why might that be interesting? The last thing we can do is check the uncertainty principle, which is that your uncertainty in momentum, uncertainty in position, is greater than or equal to h bar over 2. And one of the things that's beautiful about this class, rather than like modern physics and some of the simpler treatments of quantum mechanics, is once we start thinking about Fourier transforms, we can understand much more about what's going on here. That if we transform this in Fourier space, what's interesting is we actually get a Gaussian in momentum as well. That this is kind of a special function in that way. And so you can actually have functions that have more than h bar over 2 uncertainty. But when you do out the calculation, you get this uncertainty. That this is kind of our minimally uncertain state, that you've made your Gaussian in momentum, you have a Gaussian in position, that's kind of the best you can do. If you think about it, and I'll do a separate video talking about this a bit more, that we can have really, really highly uncertain states of momentum that are very, very certain in position and vice versa. And that really just comes from that Fourier transform. So I hope this at least shows you fully the calculation then for uncertainty in position, for this Gaussian. Again, if you've studied Gaussians before, that number should make sense. And then you could really do that momentum expectation value on your own to then see that this is true. It's equals.